Hello, the internet. Since we are in between rounds 1 and 2 of our board game tournament, I'm going to take a slight break from the board game tournament, in part because I was a little bit sick this week, so we're only about halfway through the North Division, to do a science/science fiction video. I am an astrophysicist, and so I do understand a few really deep science concepts. So what I'm going to do is I'm going to take the science as we know it, or as we think we know it, and I'm going to try to push it to its extreme to the point where it becomes basically science fiction. Some of the things I'm going to talk about are actually sort of beyond science fiction right now, or in other words, that we haven't quite gotten to the point where they are in science fiction yet. But maybe in the next decade or so will be. And maybe because of this video, who knows? That you may be hearing it here first. So I'm going to talk about two things. I'm going to talk about quantum caverns, which is a term I've coined myself, and how that can lead to quantum drive, which is a term that I think has already been coined. These are two ideas you don't really see quite in science fiction. You do see things similar to them in science fiction, but not exactly correct. Now, what you're seeing on the screen right now is a XY coordinate grid where we instead have two distances. We have two different dimensions of time. Ti is imaginary time, meaning the square root of -1, and tr representing real time. So what I want to talk about first is quantum caverns. So sort of think back to the movie Hypercube, where you have a set of cubes that are actually four-dimensional, not three-dimensional, but the people in the movie can only really see the three dimensions. They don't understand that they're also traveling through time as they're traveling around in these cubes, and they actually go around in loops. This is sort of an example of a quantum cavern. So imagine an area where when you travel around to different cubes, you don't just travel through real space in real time, you also travel in imaginary space in imaginary time. And this is something that science seems to agree with. What I'm showing here, this circle, now I'm being a little bit lazy here. The circle represents delta t and not actual t. But what we experience as time, there's actually two dimensions of time, imaginary time and real time. We experience, from our perspective, real time. And as you warp space by either traveling close to the speed of light or traveling very close to the event horizon of a black hole, what happens is that your time gets dilated, which means the real time you experience shrinks. And that might very well be a phase transition from real time, what we see here, to imaginary time. And so what you see, this circle is radius 1, effectively, in that if you travel close to the speed of light, the real component of your time is 1 over gamma, where gamma is the dilation factor in relativity, where your total energy is equal to gamma mc squared. So this is real science. But then if you do the triangle, then the imaginary part would be v over c. So if you're traveling 99% the speed of light, you'd be traveling 99%, 0.99 ti, and then 1 over gamma, which for 99% the speed of light is about 7. So you'd be traveling 1/7 real time. So that's how that would work. Now, what we don't know is if you could go to these other 3 quadrants where one of the times would be negative, either real time in these bottom 2 quadrants or imaginary time in these left 2 quadrants. But if that could happen, you could hypothetically do a loop in time and go all the way around and come back to your original starting position, both in time and possibly in space. Now, if it sounds like I'm trying to recap the movie Groundhog Day, Groundhog Day would not be a quantum loop. I'm coining another term, a quantum loop, because when he gets back to his original time, he's not already there. So a particle that could travel around in this quantum loop when it gets back to its original starting part in time, it was already at that spot and it would still be there. Now, I know for a TV movie that would be really weird and bizarre to do, but the reality is that you would have two of you now. Now, what Groundhog Day it would be more of a quantum spiral, meaning that when you get back to your original time and space in real space, you've either changed your position in imaginary time or you've changed your space in imaginary space so that you're in effect in another reality, and that you're just looping through different realities. And that for each reality, you would disappear, or someone from another reality that was similar to you would then show up to that reality. In a quantum tunnel, you would loop around, and then there'd be two of you. You loop around, there'd be three of you, and then you loop around, there'd be four of you, and then five, and then six, etc., until there was an infinite number of particles. For someone who's not in the tunnel, if they looked into the tunnel, they would see a point in space and time where something is emitted in virtually every direction simultaneously. Maybe not equally probable in every direction, because there'll be some directions that'll be more probable than others, but you'll see an infinite number of particles emitted at the same time. Now, this is reality, because when a photon is emitted by an atom, that photon simultaneously is emitted in every single direction until it runs into something, and then it was always going in that direction. So we do see this in the quantum realm already, because for light, there's no real time for light because you're traveling the speed of light, so time would be imaginary if it existed at all. So that's what you would see. You'd see something going in every single direction. Now, why would a quantum tunnel be important? Well, quantum tunnel would be important because then that would allow you to mess with the laws of probability. You're probably familiar with Schrodinger's cat, which is in a box with a atom that if it were to degrade, to radioactively decay, it would kill the cat instantly. And so the cat is both alive and dead at the same time in the box until you look inside it. As they say, curiosity killed Schrodinger's cat. And that's true. There's always a probability. That probability does change with time until you look into the box. And so typically there'll be a probability things happen. But if you set up your quantum cavern correctly, you could get it to run until you get the effect that you want. Now, why would this be important? Because once you can manipulate quantum mechanics, the probabilities of quantum mechanics, then you could do something called quantum drive. So you're probably familiar with warp drive. In warp drive, you are moving space and moving with the space. You can either move through real space, and that is warp drive, or you can go through imaginary space, which is hyperdrive. Either way, you travel to your destination much quicker because there's no speed limit to how fast space can travel, only how fast you can travel through space. And so you get to your destination much quicker. But you do still have to travel with some amount of time, and it takes a ridiculous amount of energy to do this. Even more than relativity. It could take the mass energy of a planet to activate warp drive, which is just an insane amount of energy. However, quantum drive would not require a lot of energy, just whatever energy required to be able to set up and maintain your quantum tunnel. So what quantum drive does is takes advantage of something called quantum tunneling. Now, in the core of a star, the only reason we get nuclear fusion is because when two protons approach each other, there is a tiny chance that they'll actually be in the same location. There is an uncertainty in the position of the object. This is a universal error bar, if you will. This is not a measuring error, human error. There is a literal error bar in the position of everything in the universe. Well, so when you say a particle is in a certain position, it's most likely to be there, but it has a small probability of being somewhere else. And the further you are away from that point where you think you're at, the much lower the probability there is of you actually being there. So, for example, the probability of me actually being on Mars right now and not on Earth is extremely low. Like, we're talking 10 to the, we're talking, Google to the powers of huge numbers here. So ridiculously small probabilities. But if you could manipulate those probabilities, then you could go to anywhere in the universe instantaneously. Now, the only real science fiction that's done this is A Hitchhiker's Guide to the Galaxy, and they call it improbability drive. And, of course, they do it comedically and have fun with it. But improbability drive is quantum drive. That's what that is. It's quantum drive. And so quantum drive could take you from any place to any place. All you have to do is find a way to manipulate the laws of quantum mechanics and the probabilities to basically quantum tunnel through the universe. And that's what a quantum cavern can potentially get for you, is the ability to create that quantum tunneling over very large distances. So that's it for this video. Hopefully you found this a little bit interesting. The one person who's not me who will watch this video, if we get that many. Maybe some year in the year 2050 when people are actually wanting to search for quantum drive, maybe they'll come across this video and laugh at how right or how wrong it was. It'll probably be a little bit of both. They'll look at this and be like, that's silly, imaginary time doesn't exist, even though it was predicted by Stephen Hawking. And I'd like to think that Stephen Hawking was probably right. And if, you do the math inside a black hole, time's imaginary. So, all right, so that's it for this video. I'll have a new video next week. That will be the North Division of the second round North Division. We've got to get through Twilight Imperium, and that's going to take forever. We've started the game, and it's going to take all weekend. Yeah, for those who don't know, Twilight Imperium is a 3-hour game for 3 players minimum if you try to play quick. And my kids can't play more than an hour at a time, so we have to break it up into stages. So, yeah, it takes a whole weekend of playing 1 hour and then coming back to it 4 hours later and then playing an hour and coming back to it 4 hours later. So, until then, enjoy.